Welcome to another A-Level Computer Science lesson with Teach All About It. My name's Holly and I'm going to be taking you through the Langton's Ant algorithm. So this lesson is a practice algorithm if you are studying the AQA A-Level Computer Science and specifically for the 2026 skeleton programme. So before we get started, a little disclaimer, you do need to be aware that the code that you're about to see is not the live skeleton code. This is some practice code and it has been created as an example to actually show the algorithm that we're working with. If you do need a copy of your skeleton code for the AQA exam, you will need to ask the teacher where you are sitting your exams. So another disclaimer is that I have no prior knowledge of the exam content, so any predictions here are purely speculative. This is just an algorithm that I think will work really well with the current skeleton code. So some advice before your exam is to familiarise yourself with the skeleton code. Do make sure that you have got a copy downloaded and that you have multiple copies so that you can then revert back to a clean copy of the code. And when we talk about a clean copy, that means a copy that doesn't have any changes. Make sure that you are testing your knowledge by trying out as many different practice questions as you can. So this is just one example of something that you might be able to embed into the current skeleton code. And the other thing is to make sure that you are timing yourself as you revise. Whilst you are practicing for section D, you're going to want to make sure that you know how quickly you can code. So you need to be aiming to complete that section in approximately 40 minutes. So how many questions can you complete in 40 minutes? So throughout this video, I'm going to be using a lot of technical terms which you should already be familiar with. And these are the technical terms that you are going to come across in your paper 1 exam. So this is our object-oriented reminder that we are going to be talking about multiple classes and objects. So a class is a description of an object or a blueprint. It tells us what that object will look like in terms of its attributes, which are its variables, and its methods. And the methods are all of your subroutines, so your functions and procedures that are attached to a class. An object is an instance of a class. That is where you have given your variable values. So you have actually created something from your class. So the object is real and the class is a description. Within that, we're also going to be talking an awful lot about encapsulation and inheritance. And these are two things that you can see all the way through the live skeleton code. Encapsulation, we are talking about our public, private, and protected, and that is for both attributes and methods. For inheritance, we're also talking about the ability for a class to take on the attributes and methods of a parent. And you'll see this when we're talking about things like relationships, and you may well see class diagrams that show these. So inheritance is our most basic form of a relationship, and it allows you to create classes from other classes, so a subclass from a superclass. You also have aggregation and composition. And we're not going to be looking at those two terms in this particular lesson, but there will be some others that cover those as well. So one of the things that I really will be looking at for this particular example is encapsulation. So using the idea of a public attribute or method, so that can be seen anywhere. That's very similar to a global variable, but you can also apply this to your methods as well. If you are looking at this in either pseudocode or in a class diagram, look for the plus for a public. For private, that means that you can only see that within its own class. That means inherited classes can't see it. It is absolutely private to that one class. If you are not studying AQA, this is somewhere where there is a little bit of a difference. So this is very specific to our AQA A-level. If you see a minus in your pseudocode or in your class diagram, that is identifying that this is a private class. Now, if you want an attribute or method to be seen to inherited classes as well, but not anywhere else in the code, that is where you are using protected. And for that, you're looking for the hash symbol. Okay, so now we've done a reminder, let's go and have a look at our algorithm. In the live skeleton code, we have this method called advanced stage. Now this is actually an overloaded method because it's used in multiple classes. The idea of being able to advance a stage allows us to watch a version of the simulation and see what happens to the variables each time we move forward. So I had a couple of thoughts when I first saw this particular piece of the code is what objects on the simulation grid are affected by advancing a stage. The easy answer to this is almost everything. And every object on our grid also has its own version of an advanced stage. So this is one of those methods where I would really recommend going and having a look and seeing how they work, pull them to pieces. We also want to know how we can tell what just took place. And what we're looking for in terms of our outputs. And you're only really going to be able to do this by running the simulations. So in this case, the effects of advancing one or more stages in the live skeleton code is that pheromones will decay, and pheromones are first of all a class but also an object. There are objects of ants, and there are multiple types of ants. Part of those, they will grow older. Some ants, particularly the workers, they will move around the grid. Workers will also pick up and drop off food, and workers also drop pheromones when they are carrying food. So there's quite a lot going on with our ants. And the nests are made up of ants, and this is where we were looking at the relationships between different classes. So in the real skeleton code, the ants are sort of fundamental to the whole simulation, and one of those things that the ants do is that they move around the grid. Now if they're not carrying food, they are potentially following the strongest pheromone, and if there isn't a pheromone, they move randomly. So let's have a look at the Langton's ant algorithm. Now this actually is entirely separate from what you would see in the current skeleton code, but it could be something that we could implement, and it's a really good way of practicing with the current ant code. So right now, if it doesn't have a pheromone and it doesn't have food, an ant moves randomly. But if we gave it a known algorithm like Langton's ant, what we can then do is to implement something in addition to the current skeleton code that also links to the AQA specification. So the Langton's ant algorithm, it is a deterministic algorithm. And what that means is that a deterministic algorithm, when you input something, you can determine what its output will be, and every time an input is put into this particular algorithm, if that input is the same, you will see the same outcome. Now you see determinism in AQA as part of Turing machines, a part of our finite state machine diagrams. So looking at how your algorithms are deterministic is a really interesting way of looking at some of our simulations. So in this case, what we're going to do is we're going to try and implement this particular algorithm into an ant movement. So Langton's ant, it uses a grid of cells, which should be quite familiar to us. Each cell is either set as white or black. Now that is entirely separate from the current live code. An ant is placed into one of the cells in the grid. So again, we're working with a single ant on this one. So the algorithm states that if the current cell is white, the ant is going to turn to the right, and then we're going to flip the cell to black. So you can see here we've already got states. And if the cell is black, then the ant will turn left. And again, we're going to flip the cell so that it's either black or it's white. So with those very simple instructions, we can then allow the ant to move forward by one cell. So if we were to take this and actually put this into a finite state machine diagram, this would actually show us that what we're showing is we are moving the direction of our ant either clockwise or anti-clockwise. So here we've got state 1, which could be moving up, state 2, which is turning right, state 3, turning down, state 4, turning to the left. So imagine if you were literally just on the spot and turning in a clockwise motion, you could identify I'm facing up, right, down and left. So if we were to take state 1 as the starting state, that way we know where to, when we create the ant, we know which direction to have them facing. So if the cell is white, is our next thing to put into our finite state machine. So if we're in state 1 and the cell is white, we're then going to move over to state 2, so we turn right. If we are already facing right and the cell is white, what we're doing then is we are then facing down because we are turning to the right. So this allows us to visualize how to move or how to change the direction of our ant. The same applies to state 3, where we can move to the left, or we are facing the left. We're not actually moving cells at this point. If the cell is white, and again, there is your whole clockwise motion from up, right, down and left. Now that doesn't work if you are on a black cell. So we have a clockwise direction for all the white cells and an anti-clockwise for black cells. So if you are at state 2, you're then going to be facing back up to the up. State 1 will then go over to state 4. State 4 goes back to state 3. And state 3 goes all the way back to state 2. So we have our clockwise motion and our anti-clockwise motion. Now, because we are only moving anti-clockwise or clockwise by 90 degrees essentially, it allows us to then move forward by 1 cell, depending on which way that we are facing. So in this case, it is absolutely deterministic, because we can say if you are facing up, and the cell you are currently on is white, you will end up facing right, and then you will move forward 1 cell. Okay. The rest of this online lesson is going to be using some online code that I have created for you. So you can download a copy of this either by scanning the QR code that you can see on screen now, or down in the description there is a link to download that. There are also some additional notes that you can pop over onto my website to use as a full bundle, which includes a mark scheme and downloadable copies of the code. So in order to use the Google Colab, once you have got to the link or scanned the code, you are going to need to make your own copy. So you can't edit the original because that is a template, but what you can do is you can go up to the File menu, click on Save a Copy in Drive. That will save it into your Google Drive. If you don't use Google Drive, the downloadable copies on the website allow you to just enter that and have some Python code. So again, this is not the live skeleton code. This is a much more simplified version of some skeleton code. It is similar in terms of its style to the live code, but this has been developed using the Langton ant algorithm. It also uses some more visual code to actually allow you to see the algorithm running, and that's certainly something that isn't in the main code. So task 1 is a validation task, and what we're going to do is we're going to look for the method ant is in grid. So right now ant is in grid is simply returning true. That's all it's doing. So wherever that ant happens to be, we are going to be told the ant is absolutely on the grid, even if it has wandered off right off of the screen. So what you're going to do is to take the downloaded code, extend the ant is in grid method to check the current ant's row and column. Now remember, at this point we only have 1 ant on our grid, and the reason for that is to make this simple. So ant is a class, and our grid is a separate class. Our simulation is a class. So When you are adapting ant is in grid, you are validating that the ant is in the grid using its row and column. You are going to return true if it remains on the grid, otherwise you're going to return false. So you can see on here we have a large spoiler alert. Please pause the video now. Try the code on your own first, see if you can create your own validation method, and then I will take you through my answer. So this is what I have on my answer. So you can see here, this is the additional code at the top. We have our class of cell, which is very similar, but much cut down. It's very much more simplified. We do have a class of ant. I don't have different types of ants, but we do have a row and a column to identify where our ant is. Right now, it is going to move in a random direction. And our simulation has rows and columns for itself, and it also has a grid. Now the rows and columns, that is the size of our grid. So question 1 is down here, and we have already got ant is in grid. Self means this current simulation, and returning of true is just going to happen no matter where our ant happens to be. This is not helpful whatsoever because we don't actually know where our ant is. So what we're going to do is we're going to add in some code to actually validate. Now, in this case, what I'm going to do is I'm going to use a flag variable. Now, in grid is just a standard naming code. Is it in the grid? And I'm going to assume it is not. I'm going to assume it's got off outside of the bounds of our array. I'm then going to do 2 if statements. Now here, remember to use self. So self.ant. Ant in this case is an object that we have created within the simulation. So our simulation is made up of our one ant. Now ant as a class has a row and a column. So self.ant will get us the whole of the object, but self.ant.row will get us the row that ant is currently on. And the row that the ant is currently on must be 0 or more, and I'll come back and fix that. And it also has to be less than the number of rows within our simulation. So we can use self.ant.row to get where the ant currently is, and then a less than, and use self.rows to get the number of rows in the current simulation. So that first bit there needs to be self.ant.row is more than or equal to 0, because 0 is absolutely valid. So we're just going to add a few comments in here just to make sure that we have some notes to come back to. Now in the real exam you do not have to comment anything in section D. These comments would be simply for future me to come back and revise. So if our ant is indeed between 0 and less than the number of rows in the simulation, then I can then start checking the columns. So the reason I have put an if statement, so a nested if for the column, inside the row is because there's no point in checking the column if they're outside of the row bounds. So the self.ant.column looks very, very similar. It has to be more than or equal to 0, and it has to be less than the number of columns in the simulation. So at the end of this, we're going to pop in our colon, and then we get to adjust the value of in grid. So we have assumed that it was false until we have checked both conditions to make sure that it's true. Once we've done that, what we can then do is we can return the value of in grid instead of returning true, and true being just always returning true. Now it's actually set to false initially unless we find that it's inside the bounds, then we return true. This is a really good example of something that you might see in, say, a 5 marker. So you are adding in some validation, you are starting to use some of the variables within methods, and also using that self to identify it is this particular simulation or this particular ant. And this is what it should look like. So once you have completed your validation method, you'll see your little ant running around the screen as you move it. You won't actually see any of the cells changing, and you also won't see any kind of external validation. So if you want to make sure that it's absolutely working, one of the things that I would recommend is to include a print statement. So if you added a print each time you return the true or false, so just the line before, that's going to show underneath the simulation. You can actually track that. Do make sure you comment out those print statements, because it can get quite overwhelming. It is repopulating 50 times. You can see we're at stage 49 here. So if you are running this with either 30 or even 300 iterations, you're going to want to have the smallest number of print statements possible, but they are really helpful for testing. So task 2 is where you really get into the algorithm itself. And what we're doing is we're swapping the cell colours. Now that means that we're going to be looking at advanced stage within the simulation class. And what you're going to do is you are going to go and find advanced stage, and you're going to look at that method, and we're going to adjust it so that the ant changes the colour of the cell that it's currently on. So we already know that we can get information about our ant by using its individual attributes. All of the attributes in this are public. If the current cell that the ant is on is white, we're going to switch it over to black, and if it is black, we're going to switch it over to white. So again, pause the video, try the code on your own first, and then come back and I will walk you through just one version of a way that you can do this. Okay, so this is the simulation class right here. And again, we have a very cut down version of a simulation class. So advanced stage in this case, all it's doing at the moment is it is saying if our ant is not currently in the grid, just return. Now return on its own without anything following it means return nothing, return a null value. In Python, you'll actually see this as none, but generally we refer to it as a null value. So if the ant is inside the grid, what we want to do is we want to find out what cell it's on, and we want to swap the colours. So what we are going to do is we are going to create a variable which is going to hold the current cell. Now the current cell, again, simulation being a class, the cells in the grid, they are also objects. So a current cell is a grid object. So self.grid, this simulation's grid, so the array of cells that we have the ability to use getIndex. Now what getIndex does is it takes in a row and a column and it calculates where in that one-dimensional array you would find whatever you've put in with the row and the column. So if we did self.getIndex using a method that's already been written for us, what we can do is we can put in the ant's current row and column. So we've already done self.ant.row. Well, that's what we're passing in. We are passing into the getIndex the ant's row and self.ant.column, which is the ant's current column. These are all public, and if you had something with a private attribute, you would need to get a getter. So again, current cell. If we want to swap black to white, we could write our own if statement, or we could use the method that's already been created for us, which is flip color. So because it's already there, we're going to use it. It's going to make our lives easier. We don't have to reinvent the wheel. We have already created this method within a cell class. So we work out what the current cell is. Current cell holds the object, and then we can call the method for that object, which flips that colour around, and then we've done task 2. And once you've done task 2, this is what it should look like. So I'm just going to run this, And again, we're going to run it with our 50 stages, and you can see now that as our ant is moving around, it's still moving randomly, but as our ant is moving around, when it hits a white cell, it switches it to black, and when it's on a black cell, it switches it back to white. You're probably going to see this in a lot more detail if you look at the end of the code and update that for loop. It's currently set to 50 when you download it. If you set it to a much longer number, so say 300, you're going to see this in a lot more detail, and you can actually see all of the cells changing. If you switch it to a longer number than that, you'll then see that this particular algorithm, it will look really random to start off with, and eventually it's just going to go in a one big diagonal. That actually won't happen until the very end of task 4, because right now our ant is still moving randomly. So what we now need to do is we need to set a direction and set some movement. So task 3 is to set the direction. So this is the direction without actually moving the ant. So you're going to go into your ant class for this. The ant class needs to store a direction, and in this case you have been given directions are up, down, left and right. Now if you want to go back and have a look again how that direction works, scroll all the way back to the start of the video and have a look at the finite state machine diagram that we looked at the start. So we're going to have our 4 states of up, down, left and right, and then in the ant class we're going to need to have 2 public methods of turn right and turn left. Now they need to be public because they need to be callable from elsewhere in the program. Okay, so as before, pause the video, try on your own first, and then come back and I'll show you my version. So in this case, for task 3, we're going to go up and we're going to find the ant class. So you can see up here, I've got some additional constants, and we know they're constants because they're all in capitals. I'm going to create 4 more constants up here, and these are going to be my directions. I'm going to give them a count to allow me to cycle clockwise and cycle anti-clockwise. So up being 0, right, down, so 0, 1, 2 and 3. So as I go clockwise, what I'm able to do is to add 1 to a number, and it's going to go from up to right, right to down, down to left. This is where having that finite state diagram is really helpful. So clockwise and anti-clockwise movement. Again, leaving myself a comment in there just so that future me, if I'm coming back and I'm revising, I know what on earth I'm doing. So this is the direction in which we are pointing, and a reminder that this is not moving yet. We are simply saying the direction in which we should be pointing. Then inside class ant, what we are then going to do is we're going to add another attribute, another public attribute. So we're going to put a self dot direction, and we're going to set it to an initial value, and because up was our starting point in the finite state diagram, that's what we're going to set it to here. So self dot direction equals up. Every ant that is created, even though it's 1 at the moment, is going to start at up. We're still going to be using this move random. It's no longer going to be needed at the end of our program. So by the time we've done task 4, move random is no longer a useful method. But what we're going to do is we're going to keep it here to show that we have changed the code. We've created new methods which are actually going to allow us to move in a left-right direction. So for now, we are going to have created our direction of up, and then we're going to create our turn right. Now, a turn right method, again, public because we need to use it elsewhere in the code. So we still put self in there because self refers to this particular ant object, not all ant objects. And in this case, this is how I would put together the ability to move around in a clockwise direction. So self.direction, I'm changing my own ants attribute equals itself plus 1. Now I've put this in brackets for a particular reason. Initially, what we are going to be looking at is if we are turning right, which is clockwise, we are going up our numbers, so 0, 1, 2 and 3. So you can see if I'm on 0, I'm going to move to state 1. If I'm in 1, I'm going to go up to 2, and 2 goes up to 3. This is just useful comments for future me again. But if I get to 3, I don't want to get to 4 because there isn't a direction of 4. So instead, what I can do is I can use the mod operator to put mod 4, and that will look at the number that I've got there. So I do self.direction plus 1, mod 4. So if I get past 3, it will wrap around or loop back round to get to 0. And this is something that you will have seen in multiple instances of using arrays, but also you're going to have seen this when you are using a circular queue. So calculating your index, if you have to not go over the edge or not out of bounds of an array, using mod 4 or mod the length of the numbers that you're using, that is going to allow you to loop back around and avoid those critical errors. So you don't end up with those sort of horrible out of bounds errors and everything crashing. Turning left does the same thing. Self.direction is a -1 because I'm going back the other way. You can still mod by 4. So if I end up at -1, it pushes me back to 3. So here, turning left is going to move down, and this is where I'm going to go from 3 all the way back to 2. And from 2, I can go back to 1. And again, I'm turning left. Think about yourself turning around in a circle, all the way down to 0. And again, mod 4 allows me to loop if I have gone below 0. So if I go below 0, I can go all the way back to 3. And at this point, you have updated your ant class, you have created your up, down, left and right directions, and you've also created an ability to turn right and turn left and set the new direction. And again, this is just one version of doing this. You could absolutely do this with strings, and the mark scheme in this case allows for both. And this is what it would look like. So when you run the code, actually it won't look any different. And that's because you have created some additional functionality for your ant with turn right and turn left, but you haven't actually taken that direction and done anything with it. So we've not actually got the ant to move. So right now it's still moving randomly, even though it is depositing the white and the black cells. Right now it is grey just to make it a little bit easier for us to see, but we have got all of the foundations for actually getting our ants to move in the right direction. So task 4 is the final task. So task 4 is our ant movement, and you've already set up all of the foundations for this, and now it's time to pull all of the classes together. So you are going to modify the advanced stage method, and something to bear in mind is that the order in which you do this is really important, and this does reflect some of the areas in the live skeleton code. So in this case, we know if the current cell is white, we need to turn our ant right, which means we need to call the turn right method. If the current cell is black, we need to call the turn left method. Then we need to flip the color, and then finally, when we've done everything else, we need to call a new method which moves our ant forward by 1 space in the direction that we are pointing. So for the last time, pause the video, try it on your own, and then I will show you my version. Okay, so first thing I did was to go back into my classes. So we have our class of ant to start us off with. We've already done our turn right and our turn left methods. And before we said that move random was no longer needed. And that is because we are about to write the move forward method. And again, self, because it is this particular ant object which is moving forward. So in the move forward, what we're going to do is we are going to write a set of conditional statements. So in this case, if the direction of the ant, so that was the extra attribute that we created, equals up, so it is the same as the up value, then what we're going to do is the self.row. Be really careful about this spelling that you can see on the screen. Ever so easy to do in the live exam, and it can stop the whole of the code from running. So here I am using more of a pseudocode style. So self.row equals self.row minus 1. You can absolutely use self.row minus equals 1 or plus equals 1, but I am sticking more to a pseudocode version. So in this case, I'm then using an elif for the next version. So I am going around in a clockwise rotation. So up, right, down, left. You can absolutely do up, down, left, right. I'm just making this as visual as I possibly can for myself. Also, make sure that you are popping in the right attributes there, so make sure you are testing the direction and you are setting the row and the column. The other thing to remember is that 0, 0 is top left. So if we are going up, we are subtracting, down, we are adding. If we are going left and right, you are going to add to the columns, and then going left, we are going to subtract. So the reason I am using elif all the way down is that whilst a case statement would absolutely be more efficient, in Python they don't exist. So we do have to use an if, elif in place of that case statement. So if our direction is down, then our row is going to be self.row. Don't let yourself get fooled by down meaning minus. It does not. You have to add to the row in order to move down. So self.row equals self.row plus 1. And our final elif is if that direction is left. So remember, equals equals. Ever so easy again to forget that in the live exam. Really small mistakes can mean that your code doesn't run. So just don't double check all of those syntax errors that could possibly be just typos. So left is going to again send us minus 1. So this move forward is now ready to use. So we have a turn right, a turn left, and a move forward, and we are going to now put that into the advanced stage method inside our simulation class. So in advanced stage, we've already checked if the ant is in the grid. We've also done the swapping of the colours of cells. Now what that meant was that current cell already holds the object for the cell that the ant currently is in. We've then flipped the colour and then we're moving. So what we can do is to add a little bit of white space in between finding the cell and then flipping the colour. And I really would recommend, especially in the live exam, for you to add in that white space and make it easier to read, because if you cramp all your code together, as much as it's easier to take a smaller screenshot, it does make it harder to read. So we've been told to put the ant in the right direction, then flip, then move it forward. So we're going to create an if statement here to say if our current cell, remember that this is an object of current cell, if its colour, which is an attribute of a cell, is white, and again, careful of the spelling, then what we are going to do is we are going to turn our ant right. Now our ant is an object in the simulation, just like we saw right at the beginning. So self.ant, but instead of .row or .column, we're going to do self.ant .turn right, because we've now created that public method. Remember to put your brackets in there because it is a method. There's no option other than turn right or left. So if it's not white, then what we're going to do is we are turning left. At the bottom there, we then have self.ant.moveRandom. Now we said that that method was no longer being used, so we got rid of that and we changed it into move forward. So all we need to do here is change this into self.ant.moveForward, converting it from the random movement that we saw before into looking at its direction and then moving forward using the direction. And that's the part that brings everything together. So you put all of this foundation in, and one line is the thing that's actually going to pull it all together and actually make it work. So you can see here, when we run our code, it's no longer moving in that sort of random all over the place direction. It's moving just one square at a time, and it's now using that direction. It's turning and moving based on the algorithm that we've now provided it. And if you want to see that happen in a little bit more detail, change that 50 in the for loop right at the end up to 150, 300. I put it at 150 purely for the sake of the video. And you can see you're just getting a little bit more, and you can see it's just starting to go diagonal now. You will need to put it right up. That iteration needs to be really, really long in order to show the full algorithm. So it takes a little bit of time to build up, and then eventually you will see that the ant will just travel in a single diagonal line. So once you have finished your code, your next challenge is to see how many iterations it will take to go in a diagonal line. If you found this helpful, you can get a full revision bundle which includes the code for all of the tasks, and also an example of a mark scheme for those tasks over on my website at teachallaboutit.uk/shop.